Welcome to an adventure on planet formation with near-infrared interferometry. My name is Kammerer, and I'm currently a PhD student at ExoGRAVITY and ANU's Maelstrom Observatory in Canberra. And next year I'm going to move to Space Telescope Science Institute for a postdoc. While I did single-dish kernel phase interferometry at the beginning of my PhD, I came across long baseline interferometry here at ESO, where I now have the pleasure to work with Sylvestre Lacour and the ExoGRAVITY team, which is responsible for most of the content that I'm going to show you today. So the ALMA images of HL Tau heralded a new era for protoplanetary disk science, and we are now witnessing another leap forward with the first direct detection of an exoplanet by optical interferometry. With the gravity instrument at the VLTI, we were able to detect the planet HR8799e, which is the innermost planet in this fascinating system of 4 directly imaged gas giants. Gravity enables us to obtain K-band spectra and very precise astrometry of exoplanets, which enables us to study planet formation, as I will show you in the next few minutes. Let's start with the famous directly imaged gas giant Beta Pictoris b, which is about 23 million years young and only 20 parsec away, which makes it an ideal target for atmospheric characterization. By combining the light of the 4 UTs, at Paranal, we were able to measure a K-band spectrum of this planet at a spectral resolution of 500. This gravity spectrum is shown in black and consistent with the GPI spectrum from Chilcote et al. 2017, which is shown in orange. Due to the higher spectral resolution and the smaller uncertainty of the gravity spectrum, we start to see absorption bands, for example of carbon monoxide at 2.3 to 2.4 microns. With Paul Mollier's spectral retrieval code Petit-Rat trans, the C/O abundance ratio of Beta Pictoris b could be constrained to about 0.44, which is very exciting since it enables us to infer the planet's formation history. If the C/O abundance ratio of the host star is assumed to be solar, which is about 0.55, a significant enrichment by planetesimals is required to lower the C/O abundance ratio of Beta Pictoris b to 0.44. For a massive planet like Beta Pictoris b, formation via gravitational instability would happen too fast to allow for such an enrichment. Only in the core accretion scenario, a sufficient amount of planetesimals can be accreted. This plot shows the C/O abundance ratio of Beta Pictoris b as a function of the mass of accreted solids in the core accretion scenario, and shows that for a formation somewhere between the water and carbon dioxide ice lines, a reasonable amount of about 100 Earth masses would need to be accreted in order to explain the observed C/O abundance ratio. Speaking of Beta Pictoris, in August 2019, Anne-Marie Lagrange and her collaborators announced evidence for an additional gas giant in this system based on radial velocity data, so that in February and March 2020, we again pointed the 4 UTs at the Beta Pictoris system. Now, gravity is a fiber-fed spectrograph, and in order to image exoplanets, we need to know exactly where they are and place the fibers on top of them. The diameter of the fibers is about 50 milliarc seconds, which gives us a small error margin for the position of the exoplanets. And here, we put the fibers on the positions which the radial velocity data predicted for Beta Pictoris c. And in fact, Matthias Nowak and his collaborators were able to directly detect Beta Pictoris c, which you can see as a yellow peak in the images here. The weird stripe pattern is just in the PSF of the VLTI interferometer. It looks a bit like a superposition of the pattern which one gets from Young's double slit experiment, and that's pretty much exactly what it is. It is noteworthy that gravity achieves an astrometric precision of about 100 micro-arcseconds, which tightly constrains the orbital parameters of Beta Pictoris b and c. Together with Anne-Marie Lagrange's radial velocity data, we obtain slightly eccentric orbits for both planets, and the dynamical mass of 8 Jupiter masses for Beta Pictoris c and 9 Jupiter masses for Beta Pictoris b, which is consistent with, but at the lower end of, the mass predicted by the spectral retrieval. We can then compare our results to models of young substellar companions. Given the precise dynamical mass estimate and the radius from atmospheric modeling, it seems like Beta Pictoris C, which is shown by the blue dot, is in better agreement with the formation by core accretion than gravitational instability, since the latter predicts two large radii, as shown by the hot start Amos-Kont models in red. Next, we will look at the two young protoplanets in the PDS-70 system. On the left, you can see our orbital solutions for PDS-70 B and C with a zoom on the gravity data points, illustrating the roughly 100 times better astrometric precision than what has been possible before. On the right, you can see how Jason Wong and his collaborators could put a dynamical mass constraint on PDS-70b by assuming that the orbits of the two protoplanets need to be dynamically stable. While the mass of PDS-70c remains unconstrained, PDS-70b is constrained to less than 11 Jupiter masses. Another fascinating thing that gravity enables us to do is studying the apparent size of exoplanets, very similar to measuring stellar diameters in the early days of optical interferometry. While both PDS-70 B and C appear unresolved in our observations, we can put upper limits of 50 and 80 Jupiter radii on their size, constraining the size of a possible circumplanetary disk to below 1/10 of an AU, consistent with theoretical models of the circumplanetary disk around PDS-70b. Last but not least, I would like to talk about the reddest known substellar companion, HD 206893b. Discovered in 2017 with Sphere, its color is redder than that of any other known planetary mass or brown dwarf companion. And both Delorme et al. 2017 and Ward Duong et al. 2020 have proposed that extinction by dust in the immediate vicinity of the object could cause its red color. Our team obtained a gravity K-band spectrum of HD 206893b, and we fit the entire available data with atmospheric models to which we have added additional extinction by anstatite dust. With these models, we obtain good fits to the SED of HD 206893b and infer a relatively low mass and very high extinction. Moreover, by simultaneously fitting the dust parameters, we can put constraints on the maximum grain size, for example. If we compare our atmospheric model fits with Amos-Kont evolutionary models, we obtain a twofold solution. On the one hand, an older, more massive brown dwarf, consistent with the results from the Sphere Shine team, and on the other hand, a younger, less massive exoplanet consistent with radial velocity data of the system. It is also interesting to highlight that this radial velocity data predicts another massive companion interior to HD 206893b, and the gap detected in recent ALMA data suggests the presence of a third, lower mass companion further out. The good news is that there is more to come. Gravity Plus has just been selected by ESO to start a Phase A study in order to become ESO's next VLT facility instrument. An adaptive optics upgrade and vibration control will increase the stability and sensitivity of gravity in order to give access to smaller and closer-in planets, so that with Gravity Plus, we will be able to directly detect many of the planets inferred from Gaia astrometry. At the same time, Denis Dufresne and collaborators are starting to build a nulling interferometer for the VLTI, funded through an ERC grant. Simulations by Alex Wallace and Mike Island have shown that such a nulling interferometer would significantly increase the yield of young giant exoplanets in the process of formation. The nearest star-forming regions are more than 100 parsec away, and the peak of the giant planet distribution is located within about 5 AU, emphasizing the need for high angular resolution. It is noteworthy that even with the much smaller auxiliary telescopes, nulling interferometry outperforms METIS at the ELT. So the take-home message is that near-infrared interferometry is growing mature. With gravity, we can now measure high-quality spectra and precise astrometry of exoplanets, which enables us to study their atmospheric composition and formation history. Moreover, since nearby young moving group targets are rare, and the nearest star-forming regions are more than 100 parsec away, while protoplanets like PDS-70b are comparatively bright, resolution matters more than sensitivity. Gravity Plus and Hi-5 will give us everything we need for finding more such objects. Thank you very much for staying until the end, and I'm happy to answer your questions offline. Goodbye and stay safe.